Okay, in this video I'm going to talk about the average versus instantaneous rate of reaction. Recall from the last video we talked about how since the reactants in a reaction get used up over time, the reaction rate will naturally slow. There's less likely to have a collision between reactants as they get used up, and so it's less likely for the reaction to occur as time goes on. Most rates of reaction, if we look at it from a reactant point of view, let's just stick with reactants, will start fast and slow down as time goes on. So this would be the concentration of the reactants, and this would be time. What that means then is that the average rate of reaction and instantaneous rate of reaction are two completely different things. The average rate of reaction looks at the total change in the concentration of the reactants or the products over the total amount of time. If we want to find that rate, we can use just the endpoints and imagine drawing a straight line that goes from one endpoint to the other endpoint. When we do that, ignoring the curve of a graph but just looking at connecting two endpoints, we call that a secant. And so the average rate of reaction would be the slope of the secant. I would take this as my T1 and C1 point, and this as my T2 and C2 point. And I could simply do rate is equal to, now keep in mind I've done this from the reactant's point of view, so negative C2 minus C1 over T2 minus T1. And that would tell you, if I consider all of these times, if I average out all of these rates, the average rate of reaction in the first, I don't know what, like 5 seconds or something like that. The instantaneous rate of reaction instead looks at an individual point in time. Let's take this point. Let's say we're interested in the average rate or the instantaneous rate of reaction at 1 second. Here, I don't want to take into account what's going on down here or what's going on up here. I want to focus just on this spot. And I'm going to use something called a tangent. A tangent is a line that represents the change in a curve at one point on the curve. So what I want to do is I want to imagine how this curve is changing at that instant and extend that outwards. Some math people would say that that tangent is a line that will touch the curve without ever crossing it. So it comes right up on the same slope as it has at that point and then heads off on that slope, and since the curve curves away on either side, that line won't touch or will never cross, it will only touch. I like to think of it this way. If I have a curve and I'm interested in the instantaneous rate of change at this location, I find it useful to look at that location and try and block out the rest of the curve. The more of the curve I block out, the more that one spot looks like a straight line. And so if I can imagine blocking out the rest of those curves up until just that instant of change and then extending that instant of change right there, that's how I think about getting a tangent. With this tangent in hand, that represents the rate of change at that point, so the instantaneous rate of change is the slope of the tangent. I want to take 2 points off of the tangent. I want the 2 points to be on either side of the point of interest. So here I might use this as T1 and C1, and this as T2 and C2. In general, if I go a little further away from my point of interest, if there's a little bit of issue with my tangent, I can sort of average it out by going a little further away. That being said, you're watching this as part of a course, so just be aware that, of course, I know that your tangent isn't going to necessarily match my tangent exactly. And so on any sort of evaluation where you're trying to do this tangent, I'm going to look at the tangent you drew and your method to determine if you did it right, not your absolute final answer. So I think we're ready to see an example of this. So here's the same random graph that I generated. We're imagining some sort of reaction where hydrogen gas is being used up and it starts at a concentration of 1 molarity and is going down a time, and we see that the reaction rate is happening faster at the beginning and slower at the end. And we're going to determine the reaction rate for the first 8 seconds, and then we're going to determine the instantaneous reaction rate at that 1 second. So first we'll do the easy one. I just use the end points for an average. So for T1 I have 0 seconds. For C1 I have a concentration of 1 molarity. And at T2 I go all the way to the end of my time period, 8 seconds. And I have a concentration, C2, it's not quite 0.1, it's a little bit above it. I'm going to call it 0.12 molarity. That's a little bit of an estimation, and another place where your solution and my solution might differ slightly. My rate is going to be equal to negative, because I'm dealing with reactants, C2 minus C1 over T2 minus T1. So negative 0.12 molarity minus 1 molarity divided by 8 minus 0 seconds. And I'm going to get 0.11 molarity per second. I could write this in a bunch of different ways. Recall from grade 11 that molarity really means moles per liter. So I could write this as 0.11 moles per liter per second. To me, this is the most clear statement of what these units really mean. Or 0.11 moles per liters times second is also acceptable. What does this mean then? This means that on average, in the first 8 seconds, 0.11 moles of the hydrogen gas were used up in every liter in every second. So if we had 1 liter of this product and we allowed it to go for 1 second, on average 0.11 moles would engage in the reaction. Now the instantaneous rate of reaction. This is a little harder. We're interested in this point at 1 second. So the trick here is I'm going to try and ignore all the parts of the curve except for at that 1 second. And then I'm going to look carefully, and I'm going to try and extend my line based on the shape of that curve at that 1 second. So something like that. Now I'm going to use this point right here and this point right here. And I'm going to say that I have a C1 of about 0.95 molarity, T1 of 0. A C2, I don't know, what do you think that is? 0.25 molarity and a time of 3 seconds. Again, there's going to be a little bit of variability to the solution, but it's really the method that's the important thing. So the rate is equal to the negative C2 minus C1 on T2 minus T1, where this time we're taking points off of our tangent. So negative 0.25 minus 0.95, 3 minus 0 on the bottom. So 0.95 minus 0.25, all divided by 3. I get a rate of reaction of 0.233 molarity per second. Not surprising, this is a little bit bigger than my average rate. I'm dealing with the situation at the beginning, so I'm dealing with when this is changing a little bit faster. And so I get a reaction rate, which means if I had 1 liter of this product, at this instant I would expect 0.233 moles of it to disappear in a second. So an average tells us what's happening over the whole time, ignoring the curve. Instantaneous looks at the curve, but at one specific point. The thing we call that straight line that joins those 2 points for an average is a secant, and at an individual point we use the tangent to the curve to come up with that average rate of, or with that instantaneous rate of change.